Hello, everyone. Thank you for joining DataCon LA 2021. Welcome to the AI ML Data Science track. My name is Eli, your host, and your co-host today is Stephen. We will be moderating the chat and Q&A for you during the session. Today we have as our guest Gasia Atashian, and she will be talking about building a robust fraud detection system. She is a data scientist at DISQO. Gasia is a data science and machine learning engineer, innovative math modeler, and coder with over 4 years of industry experience in data science, engineering, and technology. Gasia is a data scientist at DISQO, where she uses her expertise and knowledge to develop fraud detection systems, customize attribution models, and contribute to data-driven business decisions. Gasia is a significant contributor to DISQO's data science team, has a technical background in computer science, and holds a graduate degree in data science. Without further ado, I'll hand this over to the speaker. Thanks for being here, Gasia.
Thank you very much for the introduction. Let me share my screen. Hello, everyone, and thanks for tuning in. I would like to thank DataCon LA for organizing this wonderful event. My name is Gasia Atashian, and today I will be talking about building a robust fraud detection system. I'm a data scientist and machine learning engineer. Throughout the years, I have worked on a variety of projects, including but not limited to anomaly and fraud detection, demographic inference, product categorization, and many more. I have participated in all the phases of the project, from defining the problem to deploying the models. For the past year, however, my main concentration has been revolving around building a robust fraud detection system. Currently, I work at DISQO, which is an audience insights platform fueling brand growth with complete and actionable insights into human experience. DISQO was founded in 2015, backed by VC with more than $100 million investment, and has offices around the globe with more than 300 employees, as well as millions of customers. One of the products that DISQO owns is Junkie, which is an online market research community that delivers data and analytics to the market research industry. Junkie has more than 20 million users with more than 100 million completed surveys. So for today's event, I will be discussing the fraud, why is it rising, what to do in order to build a robust fraud detection system, and how to deploy the models. Let's start with the first question. Why the fraud is rising? The Federal Trade Commission received more than 2.1 million fraud reports from consumers in 2020. According to the data released in February of 2021, the most common type of reported fraud is imposter scams, which is defined as a dishonest person lies and tricks you into sending money to them. Unfortunately, consumers reported losing more than $3.3 billion to fraud in 2020, which is almost 100% increase from its previous year. Let alone the pandemic-related scams estimated at around $400 million. It is obvious that fraud is driven by money. Fraud happens across various industries, and the market research industry is not resistant to it. With the industry's development and various innovative features, a new evolution of consumer fraud has been emerging in financial services, giving more attention to fraud detection. Fake identities with synthetic users are common in online communities and also in existing services. So the existing services cannot prevent malicious entities from creating vast numbers of fake accounts. The impact of fraudulent activities on the companies cost them millions of dollars yearly. There are mainly two types of fraud in the market research industry: bots and human fraudsters. Bots appear to generate human survey responses or automated ghost survey scripts which jump to reward page without survey information. On the other hand, human fraudsters tend to falsify their identity in order to take surveys and collect rewards, or participate in click farms as individuals or professionals. In order to fight different types of fraud, it is imperative to build a robust fraud detection system. The pipeline of the system starts with gathering the user's data, processing and cleaning it, preparing the data to fit different models, combining the predictions, and make data-driven decisions. For this specific project, we use mainly two types of data, user profile data and user behavior data. User profile is any data related to the user profiling, saying we have the email address, the phone number, the name of the user, and so on. The user behavior is the click stream of the user on our platform. What is the date time that they entered into a survey? How did they complete the survey? What type of survey was it? And so on. We have three models in production that consolidate each other in order to cover the full journey of the user on our platform. Let's start with the first model, the dynamic labeling. So as a background, DISQO has an internal user status labeling that has been used and trusted for various internal businesses, and was the only user fraud status until a year ago. As the business grows, which simultaneously means growth in our panelists, we are not immune to an increase in fraudulent activities, and the old labels contain a lot of noise, confusing the models from learning. So we have developed our internal labeling system to control the quality of labels. Our supervised learning models have a good quality of examples to learn on. As a response, dynamic labeling has been developed as an add-on on the user status that checks different fraud indicators and assigns a cumulative fraud score that is converted to a binary. So some of the indicators include the IP address, is it from a blacklist, is it a VPN or not, what is the payment system of the user, the phone number, and also the old labeling is now only one indicator from all the other indicators. As it contained noise, now with all these indicators together, we are fighting the noise in the labeling. So with all these indicators, we give grading system for each fraud indicator, and we map them into three different buckets, green, yellow, and red, based on some assessments for each indicator. So at this point, we will have these three buckets, and for each indicator, we will assign it whether it is green or yellow or red, and these buckets are mutually exclusive, saying if we have 4 plus 3 plus 3, we have 10 questions, meaning that we have 10 indicators in here. They are mutually exclusive, so it is just write 10 indicators. After we have put everything into some bucketing, we need to convert these numbers and everything into a final label, saying that is the user a fraud or non-fraud. So in order to do this, we do a lot of trials. We consider all the possible combinations. As the red count increases, it is more probable that user is going into the fraud status, as it means that the user is grading as a fraud in almost all the indicators that we have. So with all the combinations that we put, we fit a model, and we see in which case our behavior is separated. The one that reveals the highest metrics that we measure on, we take it as the final labeling, saying that it was trial 5. So we take, if red is more than 5, then we consider the final labeling as red, or if the green is more than 5, then it will be green. And then we do some also trials here. Is the green non-fraud? Yellow, is it more as green or red? And we came up to the conclusion that green is going into non-fraud and yellow and red are going into fraud. Now, in regards to the feature engineering and data we use, our data is on the clickstream on the clickstream level, meaning that each user can have millions of records. And in order to fit it to the model, we need to convert this, reshape the data into a shape that it will be on the user level, where each user will have only one record. So in order to do this, we consider three main types of variables, and we treat based on these variables how we continue the feature engineering. So for categorical variables, we take the frequency, how many times it is being changed, and also the ratio. For example, if this click, post back, what is the ratio of each one? For the continuous variables, we divide them into pre-assigned group and calculate counts. So basically, after we divide them into pre-assigned group, it will be treated as categorical variables. And because it is continuous variables, in order not to miss anything in the data, we also consider all the descriptive statistics, starting with what is the minimum, maximum, standard deviation, and so on. Now, for the other type of data, the discrete variable, we either treat it as categorical variable or as continuous variable, depending on the case. Now, let's take an example, saying that we already converted the data into user ID and survey ID level instead of clickstream. So each user survey will have a duration, how many minutes did it take to finish the survey, and we can see that it is a continuous variable. So we pre-assign them into some grouping, so it will be the duration G. We take the grouping based on uniform distribution. Let's say we want to have 5 buckets in there, we do uniform distribution, and we put them into 5 buckets. So the 6.2 minutes, which is a continuous variable, is going into a bucket from 6 to 10 minutes. Now, this grouping is already as categorical variable. Let's say we had 5 in here, so we will have like 5 categories in the duration group. So after this point, we can just like do a counting, which is we can do like one-hot encoding, but including the count. So we will have in the bottom, as you can see, for each user ID, the duration a group from 0 to 3, how many times the user had that. And as we agreed for continuous variables, we also need to take all the descriptive statistics. So we are also taking what is the duration average, what is the median, and so on. Now we have another example there for categorical variable, saying that we have the survey type, marketing, business, entertainment. So we do one-hot encoding with the count, as we already did with the duration groups. And we just get, for example, the survey marketing, the survey business, how many times it appeared for each user. So at this point, we already converted into user level. But there is one more thing that we need not to forget about. What if the categorical variable contains numerous categories, saying that we have the instrument in the profile data and we have more than 100 instruments in there? Shall we convert it into one-hot encoding and add 100 features? This will just like add complexity to the model, and it will be very sparse data. So for this kind of variables that have numerous categories, we usually do target encoding. We do not convert them into one-hot encoding. So the target encoding, a little bit about this one. So for example, let's say we have the users and each user can have different categories. Let's say the X1 can have instrument guitar, violin, and others. We take the average of the fraud label. Let's say the guitar by itself, we can see it appears 2 times in our data. It appears in the X1 user and X5. X1 was a non-fraud, as the fraud status is 0, and X5 is a fraud. We take the average of this one, meaning 1 plus 0 divided by 2. So it will give us the fraud mean 0.5, and then we just add this weight back to the original data. So the user ID 1, X1, having the guitar, so it will have 0.5. So this is just like converting it into weighting instruments instead of the categorical variables by themselves, and we are not adding any complexity to the data. So one variable stayed as one variable. Now for feature selection and scaling, we do some feature selection via the variance. If there is not a lot of variance in the variable, we drop them, and we also drop the variables that are highly correlated with each other. And then we do some standardization, calculating the z-scores in order to be ready for the model. For the modeling part, we have multiple models in there. We have the logistic regression, random forest, XGBoost, autoencoder, neural network, and convolutional neural network. For the evaluation metrics, we first divide our data into training set and testing set with 80% and 20%. And then we decide which metrics we want to calculate. So we can calculate the ROC AUC and precision recall area under the curve, false positive, precision recall, and F1 score. So because our fraud by its usual is not a balanced data, we have a lot of imbalance saying that the fraud may be 10% and 90% are good users. So we cannot use the accuracy nor the ROC AUC because it will just like boost the data saying that we have 95% accuracy or 94% ROC AUC, but it doesn't reflect the real situation. So what we use for this imbalanced data, we mainly use the precision recall area under the curve, and it will give us a balanced result in there. And we use the precision and the recall for each of the fraud and non-fraud in order to understand how we are doing on the little details in there. So we are also interested in decreasing the false positive rate because we do not want to mistaken on the good user saying that the user is a fraud, but the user was a good user, so that we will not lose good people in there. So we do care more on increasing the precision than increasing the recall. But at the end of the day, everyone wants something like we will have F1 score, the best F1 score. But we do put a little more weight on the precision. Now, some results comparing our old labeling and our dynamic labeling for the three models, convolutional neural network, XGBoost, and logistic regression. So we can see here the precision and recall compared. For the old labeling convolutional neural network, the precision was 0.86. In the dynamic labeling is 0.8. However, we have a huge increase in the recall. In the old labeling, we weren't able to detect a lot of fraud cases. However, our precision was acceptable with 0.86. But we bumped our recall with the dynamic labeling almost 10 times from 0.05 to 0.51. Now for the XGBoost, we also see some improvement from 0.17 to 0.41, and also in the logistic regression as well. The most well-performing model that we have for now is the convolutional neural network. However, the problem in here is that it is more as a black box. We cannot interpret what features are doing well in there for each user level, why the user went into fraud or non-fraud. So we use the XGBoost and logistic regression in order to understand the feature importance, as the XGBoost can give us the feature importance as everything with one direction saying that which features are important. And for logistic regression, it gives us the feature importance with negative and positive contribution to the fraud. And what we do also, we use Shapley values in order to understand on the user level for the XGBoost and logistic regression what features contributed for the specific user to end up in the fraud or non-fraud. But the most trusted and well-doing model is the convolutional neural network. If we are fine without interpreting, we go with the convolutional neural network. And this result is, just a note, is based on the optimal threshold. So we do consider the intersection of the precision and recall, and we take that threshold and we calculate the precision recall for that specific threshold. Now, moving to the second model that we have, it is the behavior similarity. So this is a screenshot from our survey Junkie page. So when the user is on our platform, the user can see multiple surveys, how many points each survey will gain the user, and some estimation of how many minutes it will take. And the user can decide which survey to take, complete it, or terminate in some point. So in the dynamic labeling, we were just considering the count of how many surveys the user was filling. But what we are missing is the sequencing of the filling. Let's say the user 1 filled survey 1 at the beginning and then survey 2, but user 2 did the vice versa, survey 2 at the beginning and then survey 1. And what is the time gap between clicking on the surveys? So the dynamic labeling is missing these details, and as we are doing some consolidation with our models, the similarity behavior is covering what the dynamic labeling is missing. So for the behavior similarity, we are back to the click stream level, saying that this is one user behavior. The user has a click and a post back, and then let's say the user did another click without any post back, click, click, and so on. And we have the timestamp in there at what time the user did each activity. We group the time into, first we calculate the time gap between each sequence of the events, saying from 12 to 12:05, we have 5 minutes, and then from 12:05 to 12:06, we have 1 minute. And after that, we put them side by side. It will be click 5, back 1, click 0, click 1. And then we do some bucketing because the time gap will be a continuous variable. As we did before, we put them into some uniform distribution buckets, and we take some n-grams in there. So this will cover our sequence of the activities by themselves. So in regards to the n-grams, if we take, let's say, the n-grams of 3, for example, it can be click, 5, and back. So for this specific example, we are considering an n-gram of 5. However, going above 5 n-grams, we will have a lot of features. It will be more than 250,000 sequences. So it is better to limit at the 3 n-grams and the 4 n-grams. We will increase the computation, and after that, we are calculating for each tuple of users the similarity between these sequences. As for example, let's say we have the click 3 back, we just take how many counts each user had from each of these sequences. And after that, it will be just like a count data where we can calculate the similarity between them. We use cosine similarity.
Yes. Just to interrupt, there's about 8 minutes before questions.
Perfect, thank you. So continuing our similarity side, we have the cosine similarity that we use it. You can also use the angular distance, angular similarity, and so the others. So we will have for each tuple of users, what is the similarity in between them. However, just a note that calculating it for each tuple of the users, it is very costly, so you need to do a lot of optimization and parallel processing in order to be able to achieve this result. Now, as we said, this result will be on the tuple level, saying that each user can be repeated multiple times. Let's say that user 1 with user 2 has 99% similarity score, then user 1 with user 5, and user 1 with user 6. So how do we...
I'm noticing that the screen share is blank right now. Is anyone else having that problem?
I can see it.
Oh,
fine,
okay.
so.
It's just me.
Yeah.
So it's fine? Oh, okay.
Yeah.
Thank you. So for this one, we need to convert it also from tuple levels into user levels, as we did before. So how we do it, we just take the count of each user, how many times it is being repeated, saying x1 was similar to 3 other users, so the similarity count is a 3. And in order to take more granular features, do more feature engineering, we can also bucket them into saying how many similarity count were above 0.9, how many were between 0.7 to 0.8, and so on. So here we are converting them into user level. Now, the third model that we have is the email similarity. So in the email, we were saying that we are using the profiling data of the email. Mainly, a lot of people use the domain data by itself because it is easy. Is it a Gmail, Hotmail, or what is it, in order to add it to the features. But we went one further a step here, and we started doing some feature engineering on the email by themselves. How we are doing? We are calculating the Levenshtein distance in between the emails, dropping the domain. So we are only taking the first part of the email, and we are calculating the Levenshtein distance. The Levenshtein distance is described as between two words is the minimum number of single character edits required to change one word into the other. So for each tuple of the emails, we do calculate the similarity. For example, saying here we have Williams Miller, and here it is Williams without the M. The M is missing, so the similarity ratio we are getting 96%. You can see that whatever character you are changing in here, it is giving you some similarity ratio. Again, this is very expensive to do as you are doing it on the tuple level. So we have some optimization. First, bucket the emails into some similarity length, because if you are comparing a similarity length, a length of 2 to a length of 10, you won't get, because how many steps do you need to get from one to another? So bucket them in similarity length, and then do iterators, and after that do parallel processing. We have the same as before, so it will be on the tuple level with similarity percentage. We do the same conversion as we did before. Now, combining the predictions, because each model by itself is giving very good result, we are just doing an OR at the end, saying if any of the models is saying that the user is fraud, then the user is ending in the fraud bucket. Finally, on the deployment side, we use AWS servers, Amazon SageMaker to deploy our models. So we do have a separate one for the model training, and we do have for the prediction. So we use Amazon CloudWatch. It is as a cron job. It is giving the time when the model should start working. It triggers the Lambda function, and then the Lambda function starts the instance on SageMaker. And the instance, once it starts, we have a lifecycle configuration attached to it. It will know which Jupyter notebook to start. In Amazon SageMaker, everything is in Jupyter notebooks. However, everything is in Python. That's good. So it will start the training Jupyter notebook. It will read the data from Amazon Redshift, train the data, save all the model parameters on S3. And we also have a webhook integration with Slack. It will give us some notification, just giving a small descriptions, what are the model evaluation, what is the precision recall for the trained model. We do training once per week, and we use a CPU of 8, memory 32 gigabytes. The training time is almost taking 6 hours, as the convolutional neural network is taking alone 4 hours with 30 epochs. And the cost is giving us less than $20 per month. Now, for the model prediction in production, we have the same setup for the CloudWatch and the Lambda function, but this time it will trigger the lifecycle configuration, will trigger the prediction Jupyter notebook. It will read the historical data from Amazon Redshift, load the model with all the parameters, do predictions, save the predictions on S3, and after that move the saved S3 file into Redshift so that other people can query from there, and also give notifications on Slack. And we use Amazon Simple Email Service just to connect to the email and send emails to the stakeholders that are interested in the result. So we also use the memory and the CPU the same. Prediction time is taking almost 30 minutes, as we need to do the data pre-processing before doing the prediction. So the prediction time is a couple of seconds. However, the data pre-processing is taking around 28 minutes. And the cost per month, we do it as batch prediction once per day, and the cost would be less than $10 per month. Now, as a summary of what we have achieved, we solved the noisy labeling problem. We were able to consider users' full journey, integrate different models in order to get better results. And we are assuring the robust fraud detection as we are able to add different indicators to the labeling by itself. And it will do some optimization in there and it will assure the robustness. We are increasing the data quality and also we are automating the process with the deployment on AWS. Thank you.
All right. So we have Stephen asked a question. Since the data are dynamical, do you use any time series method to flag fraudulent users?
Yeah, sure. So this is very important question as we have the time series in there. At what point we should flag the user and how we are considering if we are flagging the user at some point as a fraud or non-fraud. So once the user starts the journey, let's say at the sign up or at any time, we start the fraud detection for the user. And we put a scoring in there. Let's say we are giving the user as a fraud score, but after that the user is changing the behavior and we are giving the user as non-fraud score. So we can take just like the average of what we are saying, but depending on which model is saying that the user is fraud, it can be that no matter if the user is changing the behavior, if we detected that the user was fraud at some point, the user will always be fraud. However, we are trying to do it as dynamic and try to consider the user changing behavior and try to change the final label of the user as well as the user continues the journey.
Thanks.
Thank you.
And another question from Chung Ho Yu. Is there any benchmark study to compare the predictive power of Amazon SageMaker against other predictive tools?
Yeah, sure. So with saying Amazon SageMaker against other predictive tools, Amazon SageMaker, we are not using any predefined models or functions in there. We have our own written functions and models for the fraud detection. However, if you are saying about the fraud detection tool in AWS, not specifically in SageMaker, AWS has its own fraud detection tool. We have tested it. However, our model is doing better on our data, so we didn't continue with their model, with the predefined and ready model. So in regards to the benchmark, we were seeing at least 20% precision increase with using our model than the AWS predefined fraud detector model.
That's significant. I was going to ask regarding time series and the email text, have you tried any newer constructs than convolutional neural networks like transformers for the fraud detection?
So with saying the transformers, if we can expand on that specifically, what kind of transformers are you referring to?
The transformers are used basically now for transforming text to other text or things like that, but they can also be used for identifying one thing's relationship to another. And so if the transformers are used in GPT and things like that as a construct for language translation, but they might also be interesting in changing language to fraud or something like that.
Yeah, thank you for the expansion. So there are some transformers ready in the Elasticsearch. We were trying that. They have also the fuzzy, which is underneath is using the Levenshtein distance. And there are some other transformers in the NLP where you need to do it by yourself. We were trying the Elasticsearch in order to get some ready things in from there, or specifically on the email. However, all the conversion, taking the topics to there, bring it back, it was costing us much more than if we are doing our own optimization on in Python on SageMaker. So that's why we are trying to understand how the transformers work by themselves. For example, we saw in the Elasticsearch, they are using the lavish time distance. So we are building our own lavish time distance in order to do it just like in a more optimized way, and it will cost less.
Everybody in the audience, feel free to add your questions to the Q&A.
Just a note, if you are also interested in knowing more about the benchmarks and the background comparing other papers, we also published our fraud detection in market research paper recently, so you can find it online and read about the dynamic labeling. It covers a lot of details from the dynamic labeling, and it also do a comparison with other models, existing models.
If you have the link, perhaps you can post that in the chat.
Yes.
Great.
Let me get it.
We also have another question. Do you have any statistics on false positive or false negatives?
So the statistic that we have on the false positive or false negative, we are talking about the count, because false positive and false negative, it's just giving us a count in there. So we are using the precision so that we can convert them into a percentage, and also the recall. So the precision is more focusing on the false positive, and the recall is focusing on the false negative. So as I showed throughout the presentation, let me go to that slide, we had a comparison for the false positive and the false negative. So this is the part. So let's say we are doing on the precision 80%, so we can almost say that we have 20% false positive in here. And here we see the 51% recall. So the precision is just saying that out of all the predictions, the one that we are saying a fraud, how many are correct from them, and the recall out of our predictions, how many were real fraud.
So we've got still a couple minutes, audience. So if you've got any more questions, please feel free to ask them of our speaker.
I'm putting also the paper here.
Great, thanks. So yes, the paper that Gasia was referring to is now, the link is now in the chat.
We have one more question. What roadmaps do you have for evolving the fraud detection?
So the fraud detection is more as infinite road. So we have a lot of roadmap in here, how we will improve the current models and how we can add more dynamic indicators to it. However, for the evolving in the industry, I think that everyone is just looking forward to have more quality data, especially in the market research when quality is above everything. So if we can contribute to the market research industry overall and evolving the fraud detection in there, that would be great.
So I'm going to have to end our session here. Thank you, Gasia, for your presentation and the attendees for the questions and interactions during the session. You can contact the speaker directly if there are any further questions regarding this topic. Please provide your feedback using the form that Stephen will provide in the chat box. Thank you, everyone, for joining today's presentation, and I hope you have gained some insights from this session. Have a wonderful day. Thank you for being a part of this year's DataCon LA.
Thank you very much.